Hi and welcome back. The Arduino Uno has 14 digital input-output pins. That sounds a lot, doesn't it? Well, it isn't. All these pins are multifunctional, so they're used for tasks other than pure input-output, like pulse width modulation, serial and SPI communications. We saw in an earlier lecture, that was number 60, that shift registers can be used to provide us with additional digital outputs. But what about additional digital inputs? Well, in this lecture I'll show you how to use the MCP23017 IC to easily add a total of 16 digital input and output pins to your Arduino project. The MCP23017 is an integrated circuit that communicates with the outside world using the I2C interface and provides 16 pins that can be configured individually as digital inputs or outputs. Using the I2C interface means that you can potentially add up to 128 of these devices to your project for a grand total of 2048 digital input-output pins. Any kind of simple device that provides a digital input or output can be connected. Buttons, LEDs, relays, keypads, 7-segment displays and much more. Let's have a quick look at the chip and get a basic understanding of its characteristics before going ahead with the demos. The I/O pins are arranged in two sets, or banks. Bank A is on the right, taking up pins 21 to 28, and Bank B is on the left, taking up pins 1 to 8. We will be configuring these pins as inputs or outputs and reading or writing values of them. Pins 15, 16 and 17 are used for setting up the I2C device address. You can set one of the possible 128 I2C addresses by connecting these pins to +5 volts or ground. Pins 12 and 13 are used for I2C communication, so pin 12 is clock and 13 is the data. On the Arduino Uno, you connect these to analog pins 5 and 4 respectively. Pin 18 is reset. If you take this pin to low, it will reset the device. We're keeping it to high, 5 volts, via a 10 kilo ohm pull-up resistor. Pins 9 and 10 are 5 volt power and ground. Pins 11 and 14 are not connected to anything, just leave them floating for now. Let's go ahead with the first demo. For this first demo, we'll set the port expander connected to the Arduino and write a simple sketch that sets one of the expander's pins as a digital out, then connect an LED to it and make it blink. Instead of an LED, you could use some other kind of digital load, like a small 5 volt relay switch. Here's a schematic. Notice that the pull-up resistor for pins 12 and 13 are required. These are the I2C clock and data pins. Each pull-up resistor should be around 10 kilo ohms. I'm also using a 4.7 kilo ohm pull-up resistor on pin 18, which is the reset. The LED is connected to pin 28 on the port expander via 220 ohm resistor. For the sketch, the objective is to use the I2C protocol and transmit instructions to the port expander so that the LED is turned on and off. For this, we can use the low-level functions that come with the wire library. In the next step, I'm also going to show you how to use a library. So this library is the Adafruit_MCP23017, and as you'll see, it makes programming and communicating with this IC much easier. So before we begin, it's a good idea to go and get the Adafruit MCP23017 library from GitHub. So it also contains a few nice examples. You can see how to use this library. It's pretty easy. I'm going to show you as well. So just click on the button to download it, get the zip, then install it in your Arduino library folder. Right, so it's right here. Okay, done with that. So let's start by connecting the power wiring and the address select wiring, then we'll go to the LED. So first thing is, because usually I forget, is to plug in the reset pin with a pull-up resistor. So that's pin number 18. 15, 16, 18. That is a pull-up resistor, 4.7 kilo ohm. Do the address select pins then next. It's 15, 16 and 17, and I'm going to ground them all. Since I've got nothing else connected, no other I2C device connected to the Arduino, so I'm just going to use the simplest address. All these pins are grounded. Right. Next, the pin number 13 and 14, 12 and 13, these are the clock and data pins for the I2C interface. First thing to do is to use the 10 kilo ohm pull-up resistors so that these are properly pulled up. The data sheet requires this device. So that's data, and this is clock. Clock and pin 13. Pins 12 and 13. Alright. Next, 5 volts power and ground. So ground is here. And 5 volts goes here. Right. Next up, the LED. So it is going to go to plug in like this. So the short leg goes into the ground rail. Yep. Long leg goes into pin number 28, which is GPA 7. This is bank A of the IC via a protective resistor. So I put in like that. Alright. Finally, I'll just connect the two sides, the two rails of the breadboard. So negative rail and that positive rail. Right, now we are good to proceed with connecting the communications interface. So the clock on the IC, this goes to pin 5, so this is a data pin, and then the clock, so there's a clock pin, and the data pin goes to another pin 4 on the Arduino. And last but not least, power to the board. So there's the 5 volts. And ground to complete this circuit. Well, I've done something wrong again. Something like that, because you can see that although the Arduino is connected to my computer, it basically lost power, which probably means that there's a short circuit somewhere. So let's see where. Oh, obviously, I connected the ground to the positive rail, so that's the big one. Let's see if my Arduino still works. Oh wow, still works. It's amazing. So I managed not to burn my Arduino, even though I connected the positive and ground right together. So the whole thing still works. I like it. Well, I like it, still like it because it still works. Alright, let's upload. Make sure the whole thing still works. I'm uploading to the wrong place, so serial port I want the USB, upload. Yep, all good. So let's check out the sketch. What are we doing with Sketch? So this version of Sketches uses the Wire library. So this is where the setup is happening. So initialize the I2C interface. Then I'm selecting the device. So I'm saying that I want to communicate with the device at this address, which is the port expander. And here I'm selecting Bank A. So this is the register that controls Bank A. And then on it, I'm writing a value that basically tells it to make Bank A pins or outputs. And I enter transmission here. And inside the loop, wait for 100 milliseconds, select the device that's listening at I2C address 20. And then select the register that actually controls the output pins for Bank A. And I'm writing this byte to it. So you can see that the first bit of this byte is 1. That's the one that controls the LED in that pin that's connected, which is pin GPA 7, pin 28. I've got all the others switched off. So if I take my LED resistor and remove it from GPA 7, put it into GPA 6, you'll see that that is off. There's nothing happening here because the byte that I sent to that register keeps that pin switched off. Send my data and end the transmission, and then wait for a little bit longer. Do the same thing again, but this time you can see that I'm sending out this byte, the first bit of which is 0, and that switches off the LED. But that's about it. Now, the alternative would be to use the Adafruit library to do pretty much the same thing, but of course the sketch now is a lot more concise. So the Adafruit library still requires a wire library, so I'm including both. And I'm creating the MCP object, which is going to control the chip. I begin the object, initialize the object. Then I go to pin number 7 and configure that to be an output. So in the Adafruit library, the input-output pins start with the GPA 0 being pin number 21. There's going to be pin number 1, pin ID number 1 for the Adafruit library, and then you go to 2, 3, 4, 5, 6, 7, 8. So 8 is GPA 7, pin 28. And then you switch to the other side of the chip. So you go to Bank B, and continue with this pin here being referred to in the library as pin ID 9. So 9, 10, 11, etc. up to 16. Just remember those numbers. Now in the loop, again a little delay, and I just simply use the digital write function to go to pin ID 7 and write a high value to it. Wait for a little bit longer, go back to the same pin, use digital write and write a low value to it. So much easier to control individual pins, just like you would with the normal digital pins on the Arduino itself, not the port expander.